Ladies and gentlemen, ladies and gentlemen, I feel compelled to tell you that at this moment, this recording has started. So anything stupid that you do will be recorded for everybody to hear. So, like if you want to make, funny noises or something, there we go. Also, I also feel compelled to tell you that when I'm recording, because I move around the room and the microphone is up at the front, it may sound like I'm yelling. I am, because I want to make sure the microphone catches me. So if it sounds like I'm a little loud today, that's because I am. All right. Our plan for today, in using this problem set, we are going to start putting all of the pieces together as far as measuring motion goes. We talked about at the beginning that when we're talking about measuring motion and describing motion, there are 4 things that we want to know. Where an object is, what it's doing now, what it's going to do next, and then what time is all this occurring. Up until this point, we have been looking at little individual pieces of those and kind of seeing how some things fit together, like where and what it's doing now and the time, and we've introduced acceleration, but today we want to start putting it all together. By the end of today, we are going to hopefully by the end get all 4 of a set of equations that we refer to as the kinematic equations that will relate for us the distance something travels with how fast it was going and how long it travels that distance and if it was speeding up or slowing down. Like I said, putting all of these things together. Okay? So let's start with the simplest one first. On Thursday of last week, we introduced this idea of acceleration. And we defined acceleration as the rate of change of velocity, right? Delta V over delta T. If I had my pen, it would go better, but if I use the pen, I can't use this program, so it's very, we have software and hardware compatibility issues here, so that's great. So I suppose it pales in comparison to the fact that there's no ceiling, but I suppose it pales in comparison to the fact that there's no ceiling in that room over there, but somebody was making fun of my circle, and so I had to justify. So I had to justify it. So. All right. So last week we introduced the idea of acceleration being the rate of change of velocity. That we look at the change in velocity over the time frame that change occurs, and we can tell the acceleration. And we talked about the idea that because it's delta V, that we can simplify delta V to be V final minus V initial over time. Rearranging that equation, we end up with an expression that won't show up here, apparently. Let's try that again. Rearranging that equation, we end up with this expression where we can determine the speed of an object at any particular moment in time if we know how it started, what its acceleration value was, and how long it accelerates at that rate. So we can figure out the final velocity if we know the initial velocity, the acceleration, and the time. We are going to look at one example of uniform acceleration today. Thursday of last week when you guys did your lab, I sort of indirectly introduced the idea of uniform acceleration. What does that mean if we say that the acceleration is uniform? It's constant, right? So that means, if we have a constant acceleration, physically, what does that look like? If we saw something that was constantly accelerating, what would it be doing?
It would be going like this.
On a graph, yes. Physically, if we saw it like out there in the real world, it'd be getting faster, right? It keeps getting faster and faster and faster. Or it could also be getting slower, or it could be the what's the third kind of
Turning.
turning, right? Constantly turning, changing direction, okay? So, this picture of this ball rolling down this ramp represents a motion with constant acceleration. I'm going to tell you that this ramp has been tilted in a way. This ramp has been tilted in a way that the ball experiences an acceleration of 2 meters per second squared. On Friday, we talked about that this is our unit for acceleration, right? Meters per second squared. But that really is a simplification of this complex fraction, right? Meters per second. So if we say that something has an acceleration of 2 meters per second squared, what is that telling us? If we say the acceleration of this object is 2 meters per second squared, what is that really telling us about the motion of this object? Carson, go ahead.
Every second is being 2 meters fast.
2 meters,
More.
2 meters per second faster. Okay? It's not exactly what you said. So, that's not what I heard, at least. All right. So, something that has an acceleration of 2 meters per second squared means that the velocity is going to change by 2 meters per second for every second that goes by. So with that being said, if we take a look at this ramp, this ball is sitting up on top of the ramp. It starts at time equals 0 at rest up at the top. 1 second later, could we figure out how fast it's going? Okay, that's pretty easy, right? Because for every second that goes by, we said it's going to, in this case, increase by how much? 2 meters per second. So the velocity after 1 second is going to be 2 meters per second. Clear enough? Then, after 2 seconds, what's its velocity going to be? It's going to be 4 meters per second. Let's skip this one, okay? Let's go straight to 3 seconds. What's the velocity going to be after 3 seconds then? It's going to be 6. Okay? Let's skip 3.7 and go straight to 4. The velocity at that point is going to be what? 8. All right. And then at 5 seconds, when it reaches the end of the ramp, he is not here right now. After 5 seconds, it reaches the bottom of the ramp, and how fast will it be going at the bottom of the ramp? 10. Okay, now, let's start working on some of those things that we skipped. Okay? The first one we skipped was 2.5 seconds. 2.5 seconds is how far between 2 seconds and 3 seconds? Halfway, right? From a time standpoint, not a distance standpoint, it's half the amount of time between 2 and 3, right? Meaning, if at 2 seconds it was at 4 meters per second, and then 3 seconds it's going to be at 6, halfway it's going to have to be 5. Because for every second, the velocity has to increase by 2. And if it's a constant increase, a constant rate of increase, half the time means half the increase. Okay? Good there? Now, for this one, 3.7 seconds, we could, Tyler, go ahead. Oh, okay. It's going to be what? 7.2. Okay? 7.4. Should be 7.4. So let's talk. Let's talk the hard way, and then we'll talk the easy way. Okay? All right. So we could just set up a ratio. Okay? 3.7 seconds is 70% of the time between 3 and 4. So we can kind of set ourselves up a ratio or a percentage or whatever. But before we started this discussion, we talked about the idea that we can figure out the velocity of this object at any particular moment in time after it starts if we know the acceleration value and we know how long it was accelerating. So for this ramp in particular, what was the initial velocity of this object? Up at the top of this ramp, at time 0, this object wasn't moving, so its initial velocity was 0. Then I told you that the acceleration on this ramp is equal to what? 2, right? 2 meters per second squared. And for this point in particular, the amount of time that goes by is 3.7 seconds. So we plug that all in, and I'm pretty sure we should end up with 7.4 meters per second. Good there? Now, I, on purpose, picked times that were, even times. But I could have you figure out how fast it was going 3.84762 seconds after it starts, right? Knowing this relationship between the final velocity, the initial velocity, the acceleration, and the time, we figure out how fast it's going anywhere. Good there. Now, keep in mind, this is only telling you how fast something is going. All right? Not how far it is going. What are we seeing about the spacing in between these objects as it rolls down the ramp? It's increasing, right? The spacing in between is increasing. Why, Kevin?
Because it's like doubling every time.
What is doubling?
The distance.
No.
Well,
The velocity is doubling, meaning that physically it's going what? Faster. And if it's going faster, how far is it going to go each time? You want some help? It's good, yeah. If it's going faster each second, that means it's going to go farther each second because it's going faster. Is that good?
Yeah.
Okay. All right. We okay with that? So let's start. Let's start now looking at the relationship between how fast it's going and how far it goes. The next part of your sheet there, first there's another ramp here. You guys are going to handle that later on. We talk about this object's average velocity. In the last unit, I told you that you couldn't just take two velocities, add them together, and divide by 2. Okay? And that's true. But under certain circumstances, you can do that. If an object is uniformly accelerating, if it's getting faster by the same amount each time, we can figure out the average velocity of that object if we know how fast it was going at a certain point and how fast it's going at any other point, just taking those two numbers and dividing by 2. But that only works for an object that is uniformly accelerating. In the last chapter, when we were talking about distance and time relationships, none of those objects were uniformly accelerating, so we couldn't do this. But in the case of something like this ball rolling down the hill, we can figure out its average velocity just by adding two velocities and dividing by 2 to find the simple quote-unquote average. Okay? That okay? With that being said, let's take a look at this next set. I left you guys some room to work out these calculations, but it might not be big enough for some of you to write in that space. And if that's the case, I apologize. So, all right. So if you didn't write down the velocities in the previous part on the ramp, this part might be a little bit more difficult because you're going to need those numbers. Just throwing that out there. So the first part says, what is the average velocity of motion number 1 between 2 seconds and 3 seconds? So this wants to know what the average velocity was. It gives us this interval from 2 seconds to 3 seconds. What information do we have about the velocity of the object during that interval? We know what the velocity at 2 seconds was, right? It was equal to what? And then we also know what the velocity at 3 seconds was. It was 6 meters per second. Right? Does that make sense? So if we want to find the average during this time interval, what are we going to do? Add them together and divide by 2, because that's how many velocities we have, right? So if you add these together and divide by 2, what do you end up with? Right? Does that make sense? Yes. That makes sense mathematically. Does it make sense from the picture?
Yes.
What else? This number already showed up on our picture, right? Where did this number show up on our picture? At 2.5 seconds. Because for half the time between 2 and 3, it was going less than 5. And for the other half of the time, it was going more than 5. So the average has to be 5. Does that make sense? Next, for the entire ramp, do we know what the velocity at 0 seconds was? It was 0. Do we know the velocity at the end of the ramp? Okay, we figured out that that was 10. So to figure out the average for the entire ramp, what do you do? Right? Add these together and divide by 2, right? Which is plugging them into the equation. And when you add those together and divide by 2, what do you end up with? 5 meters per second. Because time-wise, halfway down the ramp takes how long? 2.5 seconds. What's the velocity at 2.5 seconds specifically? 5 meters per second. Because half the time down the ramp it's going less than 5, and the other half the time it's going more than 5. So the average has to be 5. Confession. I was doing this in second period, and these numbers are coming up the way they're coming up, and I was like, I didn't do that on purpose. Like I didn't make you guys figure out what 2.5 was on the original ramp, and then have the numbers keep coming out as 5. I didn't do that on purpose. I just like, while we were going through the class, I was like, oh, that was really actually kind of good that it all keeps coming up the same number. But I did not do that on purpose. So. I know that it ruins my aura and mystique, but I'm pretty worried about those kind of things. So. All right, good there. Okay. Let's flip it over to the back side. Flip it over to the back side of that sheet. All right. On the back side, we start doing some math. I will not hold you responsible for how we get these equations. We really only need to know them. But just so you know where we get them from. First, hopefully this equation looks familiar. Yes? Of course. X final equals v times t plus x initial. We used it a bunch in the last chapter to represent the motion of an object moving with a constant velocity. That if we know what v is and we know how long it went, we can figure out where it ends up. Okay? We just talked about that in this case, this represents a constant velocity in the previous unit, because all of our velocities were constant. But if we know that something is continuously accelerating, right, and its average is just the average of the beginning and the end, for an object that's accelerating, we can actually plug in the formula for the average velocity into here, and we end up with this equation. So all we did was take the expression for average velocity, plug it into that previous equation. Okay? So now, if we know that something is speeding up, if we know how fast it's going at the end, and how fast it was going at the beginning, we can find out where it ends up. Sometimes we don't know exactly where it starts. So, even if we don't know exactly where it starts, we can still figure out how far it goes by taking x final and x initial. If we subtract x initial from this side, bring it over to here, we have x final minus x initial, and that gives us delta x. So this expression here relates for us how far something goes if we know how fast it was. Oh, crud. This is the mistake. So, see where this says x final and x initial? That should be v final and v initial. Sorry, everybody. I know. Please accept my sincere apology. So that's what it's supposed to look like. Delta x is equal to v final plus v initial divided by 2. Go.
Are you gonna see that on the recording?
Say again.
Are you gonna see
No, you won't see that on the recording because I just wrote it with this pen here. So. Yeah, for me to do it is going to be just, so it would probably be a good idea for you to actually write it down on your sheet, like, in that, so instead of x final and x initial, it should be v final and v initial. So now we have a way of relating how far something goes if we know how fast it's going originally and how fast it ends up going for a certain amount of time. Doesn't it? So now we can start talking about how far apart those spaces are. So if we go to the sheets.
Wait, so now I'm recording, all we're going to see is a bunch of yellow dots.
Yep. Yeah. Like I said, hardware and software are not exactly compatible right now. So, yeah, it's good. It's really good. Hardware is equipment, software is programming. So. All right. So the next set of questions, there are 3 that deal with ramp 1. Let's take a look first at how far does object number 1 move during the first second of its motion. So, if it's asking us for how far does something move, what is it really asking us for? Distance, or in this case, we'd probably go with displacement, right? So this is our unknown. All right. Other things that we know about this part of the motion. First, how much time goes by? From 0 seconds to 1 second is how much time? 1 second. 1 second. Okay? Do we know how fast it was going at the beginning of that interval? How fast was it going at t equals 0? 0. Okay? Then, after 1 second, we already established that it was going how fast? 2. So now, using that equation, right, delta x is equal to v final plus v initial divided by 2 multiplied by the time. When you plug all that stuff in there, you should get that the displacement is equal to 1 meter.
Why would we have 2 meters, 2 meters per second?
Good question, Tyler. Good question. Okay? So, remember that, and that's actually where I was going with the next question, but we brought it up now, so it's good. Remember that it's not going 2 meters per second, right? It's continuously speeding up until it gets to 2 meters per second. Does that make sense? So it doesn't actually go 2 meters per second until the very end of that first second. In order for it to travel 2 meters, it would have to be going 2 meters per second the entire time. Does that make sense? So because it's speeding up, it doesn't make it to 2 meters, not anywhere close to it, because most of the time it's going slower than 2 meters per second. Okay? With that same thing in mind, right? So next, okay? For the next question, it still wants to know how far does it go. But this time now, instead of 1 second, we're actually dealing with 2 seconds. From 0 to 2, right? The initial velocity during this time is still going to be 0, because it still wants us to take a look at it from the very, very beginning of the ramp. But now, for this segment, the final velocity is equal to what? 4. So if you plug those values into that equation, right, into this equation, right, you get that the displacement from 0 to 2 seconds is now 4 meters. So in the first second, it goes 1 meter. How far does it go in the second second?
4.
Nope. It goes 3. The total gives us 4, but the second from 1 to 2 is 3 meters. Because what keeps happening to this ball as it's rolling down the ramp? It's speeding up, right? So each second that goes by, it's going to keep going farther. Does that make sense? For the last one, the length of ramp 1, when a question specifically asks us about lengths, in order to do that, we're still going to solve for a displacement. Because the distance that the ball goes, or how far the ball goes, will determine the length of whatever thing it's rolling down in this case. How much time are we talking about now? 5 seconds, because we already established that it takes 5 seconds to get down that ramp. What was its initial velocity up at the top of the ramp? Still 0. But now, the final velocity is 10 meters per second. And again, when you plug that 10 meters per second and 0 and 5 seconds into this formula here, you should get that the ball goes 25 meters, which then has to be the length of this ramp. Good there? All right. Questions? Last one for today. That wasn't the last one for today. This is going to be the last one for today. All right. I will definitely not hold you responsible for how this is derived. You don't have to do this math. But in this equation, we have a V final. And in this equation, we have a V final. If you take the expression, here, sorry. If you take, oh, hold on. So this is V final, and this is V final. If you take and plug the one V final into the expression for the other V final, you end up with this big mess. Okay? But that all simplifies down to this equation right here. Delta x is equal to VI times t plus 1/2 a t squared. So now we have a way to relate how far we go with how did we start, what's the acceleration value, and then the time that that acceleration occurs. So now you don't have to know how fast something is going at the bottom of the ramp. As long as you know how long it takes to get to the bottom of the ramp, we can figure out how long the ramp is. Okay? So with that, this one here only has one. So now it says, what is the displacement of object number 1 during the time interval 2 seconds to 3 seconds? So this question flat out asks us for what? Displacement, so that's our unknown. What other things do we know about this little section? How much time goes by? Let's do that one first. How much time do we talk about here? 1 second, right? We want to know from 2 seconds to 3 seconds. Okay? What is the initial velocity during that section? On our ramp at 2 seconds, how fast did we say it was going? 4 meters per second. And then we said that the whole time, this object is experiencing an acceleration. And that acceleration is equal to what? 2 meters per second squared. So these are the things that we know about this little interval. We also know the final velocity, and that's okay. But using this expression, notice t shows up twice in here, right? We're looking for the displacement. This is our unknown. We know the initial velocity. We know we're looking at 1 second worth of time. 1/2 is still 1/2. The acceleration is 2. And now we plug in the time, but we have to square that time. It's just the time that's squared. And if you do that, you should end up with 5 meters. Going back to the very first calculation that we did on the other side, I asked you to calculate the average velocity from 2 to 3 seconds. And we said the average velocity between 2 and 3 seconds was 5 meters per second. So on average, if you go 5 meters per second for 1 second, how far are you going to end up going? 5 meters. There it is. All right. Tonight, here's what I want you to do. First, on the front of that page, there is another ramp. Acceleration 4 meters per second, squared. I would like you to fill in those velocities and then do the calculations of the ones that we didn't do for the second ramp. Yes?